So good morning. Let's get started. So my name is Jimmy Lin. I'm an associate professor in the Information School at the University of Maryland. And I'm going to be talking to you guys about data-intensive text processing with MapReduce. So just to calibrate the audience here, how many of you have heard of MapReduce? Okay, most. How many of you have, actually, keep your hands up, how many people have heard of Hadoop? How many people have actually written a Hadoop program? Great, okay, all right, this is not going to be boring for you guys then. Okay, so the way I want to start this off is by just a sort of a really quick recap through sort of the development of natural language processing. So one of the biggest changes over the last 20 or so years is a transition over to data-driven research. So a couple decades ago, language processing used to be done by people sitting in a room saying, well, if we write this rule and make the computer do this, then we can process these sentences. So one of the biggest revolution over the last more than a decade was this transition to letting the data speak for itself. And so there's a coherent thread of research within language processing that's just all about the data, basically. Show me the data. For those of you that have hack program in Perl, sort of made a kick out of this simple regular expression. So a global substitution of knowledge for data, right? Don't even try to be smart. Just try to throw more data at it. Okay. So there are a couple examples of this actually working out very, very well. So here's an example of a machine learning task. You guys have learned about this from the schedule I gather. So on the x-axis, this is a task in supervised machine learning. This is grammar correction. So disambiguating between that and then and then, for example, THEN versus THAN, a grammar correction task. On the x-axis is here you have the amount of training data in number of millions of words, and on the y-axis here you have test accuracy, so precision. On the you have the plot of various techniques. And this is work published in Banco and Bro, quite a well-known paper in the field, published in ACL 2001. So you'll note that basically the more data you throw at it, holding everything else constant, stuff just gets better. Right? So Banco and Bro back in 2001 made the somewhat controversial argument that we shouldn't actually try to work on machine learning techniques or do anything smart. We should just go out and get more data. So if we just get out more data, we can sort of ride this wave and to better performance. So recently, this is a more recent example is folks done work done by folks at Google. So you see, we've expanded this this plot a few more orders of magnitude now. So now we're dealing with trillions of words. So this is the size of a language model used in a machine translation task. On the x-axis here is a blue score, the standard metric for evaluation. And so you'll see, once again, that the more data you throw at it, the better the performance gets. Okay, so the theme of this talk will primarily be this question. How do you get there if we're not Google? Right, okay, so if you're Google, you have access to thousands of machines, tens of thousands of machines in large clusters. Sure, no problem. Just throw more machines at the problem. But the theme I'm going to be focused on is how everybody can, in this room, by the end of the tutorial, will be able to process information at web scale. So that's the challenge I'm going to pose to myself now. Okay, so here's a sort of the high-level overview. With the advent of cheap commodity clusters, beige boxes that you can buy from Dell, or alternatively services like utility computing where you can go out and rent machines by the hour. So this is factor number one. Coupled with simple distributed programming models, namely MapReduce is what I'm going to get into, we can get data-intensive computing for the masses. All right. So this is the high-level theme today. Okay. So I want to first start off by talking a little bit about why this is different. Okay, so, well, how do you solve these large data problems? Well, it's actually very simple. You've already learned it probably within the first 15 minutes of taking a CS undergrad course. It's all about divide and conquer. Right? So it's about taking some amount of work, chopping it up into little pieces, little work units, running them through different workers, different cores, different cores in a processor, processors in a machine, machines in a data center, etc. So the work gets done at the individual worker level, and you have to put the results back together, right? Simple divide and conquer. This naturally transitions, leads us to two problems. The partition problem, how to take amount of work and divide it up into little portions, and how to take the partial results and put them back together again. All right? Okay, so sounds easy, right? But it's a little bit more complex. So if you've taken a course in parallel and distributed programming, you realize that a lot more detail. So where the rubber meets the road is where all the complexities lie, right? So you'll have to learn about things like fundamental issues like how do you do scheduling, synchronization, in-process communication, robustness, fault tolerance. You learn all about architectural issues like Flynn's taxonomy, SIMD, MIMD machines. You learn about UMA versus UMA, NUMA versus UMA, cache coherence, etc. You learn about different programming models, MPI, message passing interface, pthreads programming model, using shared memory machines. You learn about colorful names for common problems. Dining philosopher's problem, there's the sleeping barber's problem, and the cigarette smoker's problem. But I think that one's far less politically correct, so I think people use a different name for that. And of course, you learn about different devices for dealing with all these problems. You learn about mutexes, barriers, conditional variables, producer-consumer queues, etc. Okay, so what's the bottom line? The bottom line is that prior to MapReduce, the programmer, with these previous techniques, the programmer needs to shoulder the burden of managing concurrency. Right? So the programmer needs to be up at the high level trying to solve the problem, and down at the low level trying to debug lock contention, for example. And so the point is that's just not the right way to go about doing things. Right? So I would argue that the fundamental problem, and that's what gets into problems like this. So this is a real live traffic deadlock. I don't know if this is actually doctored in Photoshop in an actual real case, but apparently it happens. Okay, so I argue that this is the problem. So what is this? This is an abstraction of von Neumann machine. Right, so this is, I argue, the problem because as we move to instances where we need to deal with large clusters, this is not the abstraction you want to be thinking about things, right? You want to be thinking at the level of how to solve the problem as opposed to managing the individual resources on each machine. Right? The abstraction that you should be thinking about is at the level of entire data centers. Okay? So this is a blueprint from Google's data center in Oregon. Okay, so you'll see that this is the Columbia River here. You guys know what's over here? That's a very large hydroelectric power plant. This is a very large dam. It will be sort of on the map right here. Okay, so the cheapest electricity in North America it is reputed to have. Okay, so large data centers. We need to start thinking about computing at that level of abstraction. Okay, so what's MapReduce all about? So if you take a large information processing problem, text processing problem, you can sort of generalize a standard recipe of how you go about crunching data. Okay, so this is typically what you do. Right, you iterate a large number of records. These could be web pages, sentences, database records, etc. You extract something of interest from each. There's some intermediate results that need to be sorted and shuffled, and then you have to aggregate them somehow and write out the output. Okay, so what's MapReduce? Well, MapReduce is simply an abstraction where you call this the map, and you call this part the reduce. Right, so the key idea behind MapReduce is to provide a functional abstraction for these two operations. Okay, so everything's still going to follow this recipe, except you specify what gets done at the map phase and what gets done at the reduce phase. What gets done on each individual record and how you integrate, aggregate intermediate results. Okay, so it's actually not a new idea. So it takes its cues from functional programming. So in functional programming, there is this higher order function called a map function. Right, so what's a map function? You give it a function and it applies it over every record in a list. Right? How many of you have, if you've done ML or Scheme or Lisp, you'll be very familiar with these higher order functions. Right? So here's an illustration of that. You get a function and you map it over a whole bunch of records. Right? Okay. The second part of it is the aggregation. So in functional programming, it's called fold, or more precisely, this is a left fold. You take another function, g, and you basically successively apply it to all the records in a particular list, which can be the output of the map base, and get out a final answer. Right, so this is something that you do for every individual record, and g is something that a function that you use to aggregate the intermediate results. So this is from functional programming, the map and fold. And all MapReduce is simply a renaming of these processes. Map still remains map, and fold has been renamed reduce. And it's essentially this style of programming at the data center level, at clusters of hundreds to thousands of machines. Okay. So let me talk about it in a little bit more detail. In MapReduce, everything operates on key value pairs. Right, so the input data is a key value pair. So for example, if you're dealing with web pages, the key might be the URL, the value might be the actual text of the page. Okay. So in MapReduce, the programmer primarily specifies two functions. So the map function and the reduce function. So the functional signatures are written very informally, but I'll describe it verbally. The map function takes an input key value pairs and generates an arbitrary number of intermediate key value pairs. Okay. What the software contract at the runtime guarantees for you is that all values with the same keys are brought together in the reduce stage and handed to the reducer, and the reducer is what you write. Okay, so the reducer takes as input a key and all the values associated with that key. Basically hands you an iterator over values. Okay. In a little bit more detail, so these are the two primary functions that you have to specify. If you want to get down into the nuts and bolts a little bit, there's also two more things that you might have to worry about. So one is called the partition and the other is called the combine. So the partition tells you where to send the keys. Okay, so you get a key, which machine does it go to? Okay, so normally you would just take a hash value of the key and mod it by the number of machines in your cluster, right? So this key will go here, this key will go there, this key will go there, and that's where the reducers happen. Okay, and combine, actually I'll talk about in the next slide. Okay, so as many of you already know by your show of hands in the beginning, Google developed this technology and wrote a paper about it a few years ago, actually many years ago by now. So they have a proprietary implementation in C++. Fortunately for us, in the open source world, there's Hadoop. So Hadoop is an open source implementation of this programming model, this style of programming that's in Java. So it's open source, so anybody could go and download it. All right. Okay, so let me illustrate basically what I just told you in pictures. It might be a little bit easier to understand. Okay, so you have a whole bunch of input key value pairs. What happens in the map is these key value pairs get divvied up and sent to the individual mappers. Okay? So you have intermediate key value pairs. Okay? There's this big sort and shuffle process by which all the key value pairs are aggregated by keys. So it now looks like this. So you gather all the A's together. Here's an A. Here's an A. You gather all the B's together. You gather all the C's together, et cetera, et cetera. And then that gets run through the reducer. And you have output key value pairs. Okay, so programming MapReduce, you do two things. You specify the mapper, the function that gets executed there, and you specify the reducer, the function that gets executed there. And everything else is handed automatically for you. Okay, so yeah.
Question: Is this process of sorting? It needs the map phase to be completely done, or
yes.
So it's there's no kind of like pipeline in it where like you might be sorting stuff.
So what happens is the output of the mapper starts getting, so these are running on different machines in a cluster, right? So what happens is as soon as the map output goes out, it gets sent to the right reducer.
So the reducer might not get all of it.
No, but the reducer cannot start until all the map output has finished. So you can think of this as a barrier, right? Because a reducer needs to know all the values that's ever going to get before it can start.
So the network traffic is done in a kind of like piecewise.
Yes.
But
Yes, incrementally. Yes, without getting into much detail, this happens in the background between the map and the reduce phases. So as I'll get to, the point is that you don't have to worry about that. This is a very large, complex sorting problem, right? You have map output that needs to go to the reducer. So mappers may generate billions, even trillions of key value pairs. They need each to be shuffled to the right place. The system, the runtime handles that for you automatically. Okay, so as I mentioned in the previous slide, the partitioner is a function that decides where each one of these key value pairs go. Right, so partitioner says, okay, A goes here, B goes there, C goes there, by taking the hash key of a particular key and then modding it by the number of reducers in the machine in the cluster. Okay, all right. So what is exactly does the MapReduce runtime do? Right, so you write the mapper and the reducer, and basically the runtime takes care of everything else. Right, so it takes care of scheduling, assigning workers to do the mapping and the reducing. It handles data distribution. I'll talk about that in a little bit. It talks about synchronization, which is basically the answer to your question. The shuffling and sorting of these intermediate key value pairs. Handles faults. Right, so if you have a cluster of thousands of machines, things are going to break, so you'll need to deal with that. The runtime deals with it automatically, and everything happens on top of a distributed file system, which is what I'm going to talk about next. Okay, in a couple slides. So here is the hello world example of a MapReduce program. So this a very simple example simply counts the number of occurrences of each word in a large collection. Okay, so imagine the web, and you want to find out how often cat occurs or dog occurs. This was the MapReduce program that would actually do it. Okay, so what do? You take as input a key, let's say URL, and the document that's the text of the web page. What you simply do is you tokenize, you chunk up each individual words, and you emit a key value pair for each word. And that's the word and 1, meaning I've seen this word once. Okay? And the reducer, what do? Well, you simply add up all the ones, right? Because that's what the runtime guarantees for you. The runtime guarantees that all the values associated with the same keys are going to be brought together. Right? So you have a word, and you have all the occurrences that are all the counts of the occurrences, and you simply add them together. Okay. So this literally written in Java is 20 lines. In fact, the boilerplate for setting up the MapReduce job is actually longer than the mapper and the reducer itself. Okay. And with these 20 lines, you can operate on any amount of data. Right? So automatically scale out to terabytes, tens of terabytes. I don't know about petabytes quite yet for Hadoop. All right. Okay, so here's what's actually going on. So you have a large cluster here in the background. You're sitting here with your user program. So what happens is you write the MapReduce program, and you submit a job to the cluster. So here's a master node that's listening and waiting for job submissions. So this is packaged up as jars that gets transferred over to the submission queue. And what happens is the master then takes over and manages everything for you. Right, so it's got to know where the input is. I'll get to that in just a bit. It's got to split the input, send it to the workers. The intermediate workers, the workers operate, run the mappers, and generate intermediate output. So that gets temporarily written onto local disk, and then remote read by the worker that's running the reducers. Okay, this is this complex sorting and shuffling process that goes on. Okay, and then finally that gets sent to the reduce workers, and the output is finally written to disk. All right. Okay. Any questions so far? Okay, great. So let me come back to this data distribution question. How do you get data to the workers? Okay. So in a traditional setup, you have your compute nodes off to the side. And then you have your data storage off to the other side. right? Something like NetApp filer or something like that, network, some type of network attached storage, or SAN or something like that. Okay, so what's the fundamental problem here? It's an yeah.
It's expensive to move data back.
Yeah, it's this is going to be a bottleneck, right? So what happens? You want to upgrade your cluster. You start buying more nodes. Okay, this link breaks because you've crashed the file server by trying to have thousands of file requests at the same time. Right. So this is a large scalability bottleneck. Okay. The solution is, well, that's not move data to the workers. That's move the workers to the data. So one of the key ideas behind this technology is don't move the data, move the process. So as opposed to moving the data to the processors, move the processes to the data. Okay, this happens is orchestrated by a distributed file system. So in the distributed file system, that all the data is chunked up into blocks, and all the blocks are stored on the local disks of machines in the cluster. Okay, and quite simply, the MapReduce runtime knows where all the blocks are, and so it says, okay, if the blocks are here and I need to map it over here, I'll just run the mapper here. Okay, so I don't need to move data around. I can simply move the code around to where the data lives. Right? Okay, and so what actually makes MapReduce work is the underlying distributed file system. So Google's version is called GFS, the Google File System. The open source version of it is called HDFS for Hadoop Distributed File System. Yep.
Okay, so if all the data is on the workers, right?
Mm-hmm.
And so the workers are busy doing
Mm-hmm.
some processes, and somebody else wants to access their data. Do the workers have to sort of interrupt to supply the data, or is it sort of taken care of so that's not a problem?
Okay, so as I'll get into in the next slide, things are kept in triplicate. So that's how resiliency and fault tolerance is handled, by keeping multiple copies. And the master node is smart enough to say, okay, this one's being operated on, and so I'll send you to this other guy. Okay. All right. So the assumptions for this is that we're not going to depend on exotic hardware. We're not going to buy very large special purpose filers that are very expensive. We're just going to buy 1U rack mounted units from Dow or your favorite company. There's going to be large high component failure rates. The system was designed for a modest number, millions let's say, of huge files, hundreds of gigabytes, files that are even terabytes in size. All right. The dominant workload is not random seeks, but appending. Right. So you think of for example, log output. Right. So logging output, you sort of never overwrite logs. You simply just append to the end of logs. So that's the dominant workload. And on the reading end, the system is optimized for very quick streaming reads, as opposed to our random access. So the whole system is optimized for a sustained throughput as opposed to low latency. Okay, so so as mentioned before, in the Google file system, and by design, the Hadoop distributed file system, HDFS, since HDFS is just a clone of GFS, everything is the files are stored up as chunks in 64 megs chunks, and you have reliability by keeping everything in triplicate, 3 copies. And the system knows where all those blocks are, and if the nodes go down, it automatically spins up replication. It says, okay, I only have 2 copies left. I better copy a block around to make sure I have 3 copies. So there's a single master to coordinate all the accesses. I'll show the architecture next slide. Interestingly enough, there's no data caching, right? Because if you think about all these, all of the typical loads, if you're going to do long streaming reads, for example, caching is not going to be a benefit anyways, right? And caching, if you do caching, you have to worry about cache coherence, and it introduces complexities. And another of the design decision was to actually have a very simple API and push off a lot of the work onto the clients, the applications that are reading using the file system. Okay, so here's an architecture there is, so here you are sitting with your application trying to access the file system. You talk to a master. The single master node is what maintains the file space, namespace mapping. Right? The mapping of the directory structure, the mapping of the file to the block locations. Okay? And what actually what happens is if you want to access a particular file, you talk to the master. The master says, OK, you can go find a copy of the data block on this particular data node. Okay? And so you, the client, say, OK, I got redirected from these are called chunk servers in GFS or data nodes in HDFS. You talk to the data nodes directly and say, OK, give me my data. And the data is passed back to you directly. Okay, so now note crucially that you only talk to the master for metadata. So you never actually move data through the master. It's directly moved by the individual nodes in your cluster. Right? Any questions? Okay, so MapReduce then runs on top of this infrastructure. So it knows where all the block locations are, so it knows how to do the scheduling of the jobs to optimize for locality. Right? Okay, and I've talked about all these. The metadata takes care of the replication, the namespace management, etc. Any questions? Are you sure? Why is it called Hadoop? Hadoop is the name of Doug Cutting, who is the creator of the project. It's the name of his son's yellow elephant. So there is the Hadoop. It's a stuffed yellow elephant. Toy elephant, yes. What's a toy stuffed elephant? Yeah, it's about this big. Apparently it's gotten totally to the kid's head. He's like 8 now, I think. So he has this whole, whole community named after his toy stuffed elephant. Not bad, I guess. Okay, so if there are no questions, let me see. Okay, I swear I'm not checking email. This is the only timepiece I have. So, although I am tempted sometimes. Okay, I'm going to present the case study in graph algorithms. Okay, so what's Google famous for? Google's one of the things it's famous for is PageRank. What's PageRank? PageRank is a large distributed graph algorithm. Okay, so it's only fitting that we sort of talk about PageRank in the context of MapReduce. Although they just came up with a recent paper to be published that apparently they've developed a whole different system beyond MapReduce for doing these large distributed graph algorithms. But I'm going to talk about how you would implement graph algorithms in MapReduce. Okay, so I'm going to talk a little bit about graph representations. Going to talk with a sort of a warm-up starter problem with the single source shortest path problem, and then going to talk about PageRank. Okay, so what's a graph? Graph, standard definition, has vertices and edges. I'm going to use nodes and links and vertices and edges interchangeably. The different types of graphs, you know about directed graphs versus undirected graphs. There may be cycles, there may not be cycles, etc. Graphs are everywhere. So everything from airline scheduling to if you want to break up the spread of avian flu or swine flu, who's the person you're going to target, all the way down to finding a job in Match.com by part-type graph matching problem. So graphs are everywhere, and of course PageRank. Okay, so how do you represent a graph? Well, there's two common representations. You represent it as an adjacency matrix, or you represent it as adjacency list. Okay, the first is adjacency matrix. So it's a square matrix, n by n squared matrix, where n is the number of nodes in your graph, and you simply put a 1 in the row and column if there is a link from I to j. Right. So in this example, you have a link from 1 to 2, so that's that. You have a link from 2 to 3, so 2 to 3, that's that, etc. So you can see how this matrix is a representation of this graph. All right. All right, the problem with this is that this is a very sparse matrix. Right, this is a very big sparse matrix. Right? So for the web, how many nodes are there on the web? Let's say 10 billion web pages, 100 billion web pages. This is a really, really big matrix. It's a really, really big matrix with a lot of zeros in it. Because for the most part, each site only links to a minuscule fraction of the number of pages that are on the web. right? So what do you do with all the zeros? Well, you throw them away, and that's how you get a adjacency list representation, right? So you simply take the matrix and you throw away all the zeros. So, and you represent it as such. So this says that from 1, I can get to 2 and 4, right? So from 1, I can get to 2 and 4. From 1, there is a link to node 2 and node 4. Right, so this representation essentially tells you who your neighbors are or what your outlinks are, right? Who you're connected to. Okay, and this is actually the preferred representation for graphs. Okay, so let's talk about how we'd solve the single source shortest path problem. Right, so given a node, you want to find the shortest path from a source node to one or more multiple nodes. Right, if you think back to your algorithms course, you'd solve this with Dijkstra's algorithm, right? But in MapReduce, we're going to solve it with parallel breadth first search. Okay, all right. So first, let's consider the case where all the paths are equal weight, and then paths of different weight will just be a very straightforward extension. Okay, so here the solution can be reasoned inductively. I'll be rather sloppy about the induction process just to give you a sketch of the algorithm. Okay, so the distance from the start node to yourself is 0. Right? Okay, so for all nodes that are reachable from the start node, the distance is 1. Right? You go 1 hop. And then, so this is a base condition, and this is the inductive step. Okay, so if you can get to, if you get to n from any of the nodes within set S, right, then the distance is simply 1 plus the shortest distance to S. Right? The idea is if you can get to me from you, then it's simply one more hop past you. So the shortest distance to you. Right? Okay. So here's how the algorithm works. What you're going to do is you're going to map over the adjacency list in your graph representation. Right, so there's the nodes and the adjacency list, the outlinks, your neighbors. Okay, and then you're going to emit. So the key. So the input key is the node ID, and the input value is your current distance, which it's either known or infinity, and your adjacency list. Okay, and what you're simply going to do is you're going to emit. For every one of the links that you can get to, you're going to emit that node ID plus 1. Okay, so what does that mean? That means I can get to myself with distance d, which means then I could get to all of the nodes that I'm connected to with a distance of d plus 1. Okay, so what happens in the reduce stage is that, remember, all the values of the same key are brought together. All right. So this says at the reduce stage, you essentially have all the costs of getting to node P. Right? Everybody says, I can go to P with this cost, I can get to P with this cost. The reducers, all those costs get brought together. And the reducer simply takes the shortest one. Okay, and with a little bit of more additional bookkeeping, you can actually keep track of the paths. But this just keeps track of the distance. Right? Okay. So what happens is then you run this algorithm multiple times, multiple iterations. Right? And so I'll get back to the second point. But here's essentially a graphical image of what the running of the algorithm looks like. You map over the graph, and you expand the known frontiers by one node. And then you run the algorithm again. You expand the frontiers by yet another node. And so on and so forth. Okay, but you might be wondering, where did the graph structure go? So we're just emitting distances, right? I've lost the adjacencies list somehow. Okay, so that's the only trick in this algorithm, is that you have to pass the adjacency list along also. And so you have to pass it along, and the reducer has to be smart enough to put together all the pieces. Right? You have the adjacency list as one piece and all the possible distances as another piece. When it gets the adjacency list, it's got to set it aside, deal with the distances, put everything back together, and write it out to disk, ready for another MapReduce cycle. Right, so you run MapReduce once, you expand the known frontier, you run it at times, it expands the known frontier again and again. Okay, and assuming you have a connected graph, you'll eventually get everywhere. Okay, okay. So this is with weight edge 1. Okay, so now an arbitrary extension to a graph with arbitrary weights as long as they're positive, because if they're negative, it breaks all rules, because you can just go around infinitely in loops and have infinitely low costs. So instead of emitting d plus 1, you emit d plus the weight of your edge, and that's it. Okay, so if you think back to Dijkstra's algorithm, how does this compare? Well, Dijkstra's algorithm is a lot more optimal in basically the total amount of computation that you have to do, because what it does is it only expands the frontier with the lowest cost. Right? It's only expanding the node that has the shortest cost, and so at each point, it's not visiting nodes that are going to be end up being longer paths. Not so with breadth first search in MapReduce. You're essentially examining all paths in parallel and letting the reducer choose the most effective one, the shortest cost one. Okay, so a lot less efficient. You should sort of think about it in a total amount of computation done. But what's the advantage? The advantage is you can throw as many machines on it as you basically have. Right? Okay. Any questions so far?
Yeah.
Yep.
Sorry.
Sure, no problem.
In the algorithm, does it start at every node and emit distances from every node, or does it just start at the start node?
You have to start at the start node, because in the distance, in the beginning, what you do is you initialize the algorithm so everything other than the start node is distance infinity.
So the first iterations are like really fast.
You're still mapping over all the nodes, but you haven't found any of them yet. So the reducer says, okay, I can't. All the distances are infinity, so it basically does nothing in the first few iterations. Okay, so let me move on to talk a little bit about PageRank. What's PageRank? The best way to describe PageRank is imagine a blind, drunk web surfing monkey that sits in front of a computer and randomly clicks links. Okay, PageRank characterizes how much time this blind web surfing monkey will spend on a particular page. Right. So in other words, it's a random walk over the graph, the hyperlink structure of the web.
Are you pressing the button?
I guess you can interpret that for part of the model. Okay, all right. So here's a definition of PageRank. I'll explain it to you, and I'll explain it to in pieces. So let's say you want to find the PageRank of this guy right here. Okay. So what's the PageRank of this guy is going to get contributions from the PageRank of all the nodes that are linked to it, right? So that's focusing. Let's deal with the equation part at a time. So that's only start with this part, the summation over PR of Ti over C of Ti. Okay. Okay. So how do we get to this node? Well, we get to this node by having the blind drunk web surfing monkey get to here. Right? So if the monkey's here, there is a chance of 1 in 3 that the monkey will get to here. Right? He's randomly clicking nodes. Right? The same for this. The same for this. Right? So then, therefore, you take the PageRank value of this guy, you divide it by the number of outlinks, 3, and this is the PageRank contribution from that X receives from T1. Right? And you simply sum over all the nodes that are pointing into X1. That's this part. That's the summation part right here. Okay, so what's this business with alpha and 1 minus alpha? In fact, I lied a bit. So the blind, drunk, web-clicking monkey doesn't just randomly surf. What he does is every time he flips a coin, a biased coin, And with some probability, he's going to surf. For some other probability, he's going to type in a random URL. Okay? And essentially teleport around the web. This is called the teleportation factor. And basically, the alpha and then 1 minus alpha is essentially controlling those two factors. It's sometimes called the teleportation factor, random jump factor, or the damping factor, if you want to sound more scientific. Right, so with probability alpha, the monkey's going to do a random jump and pick a URL out of thin air and jump to it. So that's that's the contribution of getting there is 1 over n, where n is the total number of nodes in the graph. Right? Okay, so after explaining this, how would we do it with MapReduce? Okay, so the nice property about MapReduce is that it can be computed locally, and the effects at each iteration is relatively local, right? So this will only be affected by the number of links that are pointing in, right? So it's a relatively local effect with respect to the entire size of the graph. Right, so the sketch is, okay, we're going to start with seed PageRank values. That's just establish a uniform distribution over all the nodes. And so each page is then going to distribute its PageRank credit to all its neighboring nodes. And all the target nodes are going to essentially sum up the PageRank contribution that it receives. Okay, and you just want to iterate through this process. Okay. If you think about it, this is simply a MapReduce algorithm. Right? So in the map phase, what you do is you distribute your PageRank credit to your target links. Right, you get your adjacency list, and you say, okay, I'm connected to these guys, so I'll spread the wealth. I'll spread my PageRank credit. And that'll be the key that you emit as output. Okay? In the reduce phase, well, what does MapReduce do for you? It brings up together all the values that are associated with the same key. Essentially, from the target node's point of view, you get all your PageRank contributions from lots of different sources, right? And it all gets gathered together, and you sum it up, right? And then you simply iterate, right? So PageRank is an iterative algorithm where you have a map phase and a reduce phase, and then you sort of simply iterate until you converge. And for even large numbers of very large graphs, it converges in surprisingly few iterations. For the graph structure web, a few dozen iterations will get you there, will get you to convergence.
So how do you detect convergence if only each worker performs very local computation?
Okay. Details. There are actually a lot more details, but the answer to that is there is a driver program outside of MapReduce. Right? There's a driver program that's going to set up the iteration. The conversion checking is going to happen in the driver program. Yep.
How much time does it take for one iteration?
For one iteration, it depends on the size of the graph, but for the entire web, it depends on how many machines you have. So then you can ask how many machines. A lot quicker than you think. I don't have stats on the top of my head, but this is pretty fast. Okay, let me think. I'm running short on time, so I won't go over the details. Instead, I'll talk about other interesting stuff. Okay, so the general approach for dealing with graph algorithms in MapReduce, I just talked about 2 examples, parallel breadth first search and PageRank, is this. So you want to store the graph as a adjacency list, and you want to map over the nodes, and you want to propagate your local computations around your outlinks. Right, so this is a computation that's some function of the link structure. Right, in PageRank you pass a PageRank credit off onto the nodes that you're connected to. In breadth first search, you take the distance and add 1 to it. Right, and the reduce reduce task collects the keys, which are the target nodes, and then does some aggregation computation. Right, in PageRank, it sums up all the PageRank mass that's been passed to it, and then typically for these graph algorithms, you run them iteratively until there's some convergence criteria that's met. Right? And the detail here, you got to pass along the adjacency list from one iteration to the next. Okay, any questions? Yes, Damianos, you just want to be a heckler, don't you? Okay, what's up?
Sorry. So I understood that reducers have to wait for mappers to
Mhm.
use the computation, but it looks like the mappers also have to wait for previous reducers. It looks like there is
Yes.
have a deadlock at the same time.
Well, what simply happens is there's a hard barrier. So all the mappers, the system grinds to halt until all the mappers have finished. Right? Of course,
All of them have finished.
all of them have finished. Of course, the system is smart enough to start copying because you know where all the keys are going. Right? So what happens usually is it grinds to a halt, waiting for the last mapper to finish. The last mapper finish. The key value pairs get distributed, and then the reducers are off to the races. And then some reducers finish quicker than others. There's sort of another hard barrier until all the reducers finish. Then you can start the next MapReduce iteration.
There has to be a scheduling which says after the reducers stop, then you have to start new mappers.
Yes.
It's not like you start all the mappers and then then the subsequent mappers will have to wait for the previous reducers.
Yes. But that is very easily handled by the API. Right? So basically, you get a handle to a job and you can check its status. Right? And then you simply don't start until the...
So there has to be some central scheduling.
Yes. You're talking to... you usually have a driver program that starts up the job and keeps track of its progress. Right? And by a simple polling mechanism, you can find out the progress, and then thereby, in MapReduce, you check for a convergence, and then if you need to iterate again, you start up the process again. Okay. Yep.
So the 1/n factor, is that something that's also being passed around?
That's not covered in this detail. So that's something I didn't go over. So as with many of these algorithms, to get all the details right, it's a little bit more complicated. Why don't we take this offline? I'm happy to explain it to you after, but I don't want to get into it here because it's a lot of hairier details. Okay. All right. So I'm going to switch gears a little bit and talk in general about MapReduce algorithm design. And if you are interested in getting into this, you'll soon discover that programming in MapReduce is kind of tricky. It requires you to think about designing algorithms in completely different ways. See, because here's why. Remember, all the mappers are running in isolation, right? So you don't know what order they're running in. You don't know where they're running. And you have no idea which mapper finishes first. Right? So you just submit the job and say, I want to map over all these key value pairs, this 10 terabytes worth of key value pairs, and it sort of just does it. So how do you control program flow? How do you do synchronization? Okay, this is what I'm going to talk about in the next 20 minutes. Okay, so here's how you control. Despite the lack of control over these things, you do have a couple tools in your toolbox to be able to control the execution of MapReduce algorithms. I'll give you, and this is what I'm going to talk about. So the first is the ability to hold state in the reducer across key value pairs. So for example, so what happens in the reducer is the reducer will see all the key value pairs that it's processing. And so you can essentially hold things in memory while you're processing one to process the next. That's actually a very useful trick that I'll come back to. You can hide synchronization by clever sorting of the keys. Okay, I'll talk about that also. By clever use of the partitioner. The partitioner, remember, is this function that tells you where the keys go. And finally, by cleverly constructed data structures that sort of bring the pieces of the computation together. Okay, so the motivating example I'm going to be talking about is let's say I want to build a term co-occurrence matrix for text collection. So believe there was like a section on text mining or something like that, right? This would be very useful for that, right? So what's this term co-occurrence matrix? Okay, you're given a vocabulary, you're given a large collection, hundreds of gigs, terabytes even, let's say. And you want to build a term co-occurrence matrix. It's a matrix that's n by n, where n is the size of the vocabulary. And if two words co-occur in some context, a sentence, let's say, or a paragraph, there's an entry in that cell of the matrix that tells a number of times that it co-occurs. Okay, why would you want to do this? You would do this, for example, if you wanted to measure semantic distance. Okay, so if you want to find out if these two words are similar, are they synonyms of each other, or are they related somehow? A trick that's used widely in NLP is to compare its neighbors. Right, so if this word occurs in the same context as this word, they must be related somehow. Actually, could be synonyms, or actually they could be antonyms. All right. And how do you find the neighbors? Well, you look up in this really large co-occurrence matrix. Right, so this is a motivating example. Here's a sample application, but I'm going to be talking about the very abstract problem of how do you build this really, really large matrix. Okay, if your collection is small, just put it in memory, right? But at some point in time, as your collection grows, you're not going to be able to buy enough memory to have to hold the entire matrix. No matter how clever you are in doing compression and bit packing for the matrix rows and columns, right? At some point in time, it's just going to overwhelm the amount of RAM you have on a single machine, right? So you have to do this in a distributed fashion. Okay. Okay. So the other nice thing about this is this term co-occurrence problem is a very specific example of a large counting problem. And large counting problems are essentially what MapReduce are excellent at. A large distributed counting problems, where you have a large event space and you want to keep track of things that happen. Okay, so the basic approach is that the mappers are going to be at the local level generating the partial counts, and the reducers aggregate the partial counts. Okay, so then the question is, how do you do this partial count aggregation efficiently? I'm going to talk about two approaches. The first approach is what I'm dubbing the pairs approach. Okay, so let's say you want to do co-occurrence with a sentence. So naturally, you map over sentences. And then what you're going to do is you're going to generate all co-occurring term pairs within that sentence. And you're going to emit the tuple, the pair that you observe, and its count. All right? And simply, the reducers sum up all the counts associated with the pairs, right? So each tuple essentially represents a cell in the matrix, and the reducer simply sums up the cells in the matrix from all the partial contributions. Yep.
So some words appear more often together than other words. And invariably, you're going to have to get them all in the same reducer so that they can add them up.
Yes.
I feel like a lot of the reducers may take a lot longer than other reducers.
Great. So two answers to that. One is, this is the first approach. This is, of course, going to be, if I'm going to present multiple approach, the first one is going to be the naive dumb approach. Right, so yes, we'll address that problem. The second is this use of combiner. Actually, I think I skipped talking about the combiner earlier. So the combiner, you can think of it as a mini reducer that you run directly on the output of the mappers. Right, so normally you do mapping, intermediate key-value pairs get shuffled, go to the reducers. Right, the combiner is a function that you can actually specify running directly after the mapper to do some type of local aggregation. So this will cut down dramatically on the network traffic. Okay, so here's a case where you want to use a combiner. Right, so you have all these pairs. You want to do some aggregation at the individual node level before it gets shuffled over across the network. Okay. All right. So the advantage here is it's easy to implement. It's pretty easy to understand. But there's a lot of pairs to sort and shuffle the network, right? and the network is the slowest part of your cluster. Okay, so here's another approach. This is what I'm going to dub the stripes approach. So the idea is you want to group together pairs in associative array. So instead of A paired with everything else, what you're going to do is gather up all the second place on the right part of the tuple into associative array, essentially a map. Right. So this says with A, I've seen it co-occur with B once, C twice, D 5 times, E 3 times, F 2 times. Right. So this is an alternative representation of these whole bunch of pairs. Okay, so you're still doing the same thing, except instead of doing generating pairs, you're generating the stripes, associative arrays. So you're going to still map over the sentence. Instead of generating pairs, you're going to generate you're going to gather all the co-occurring term pairs within a particular sentence and emit this associative array structure. Okay. Well, what do you do in the reducer? Well, the reducers are going to get essentially different fragments of these associative arrays. You're simply going to do an element-wise sum. Right? Okay. So if you think of the pairs approach as essentially each pair representing a cell in the matrix, the stripes approach is essentially representing each row of the matrix at once. Okay. Okay. So the advantages here, there's far less sorting and shuffling. The disadvantage is that it's a little bit tricky to understand and to implement because you have to do this associative array business. And the underlying object is a little bit more heavyweight, right? So remember, all of these objects need to be sent across a network. So they need to be serialized and deserialized. I'm getting a little bit into programming details, but there's overhead here. Right, you have to write these pairs out to the wire, and then you have to read them back in before you can do this element-wise merge. Okay? Some overhead associated with that. But however, the fundamental limitation here is the size of the event space. So imagine in the limit if this stripe, if this associated array gets so large as to not fit into memory. Okay? Well, in a large enough collection for common enough words, it's going to co-occur with so many other words that the stripe might not fit into memory. Okay, in that case, this algorithm is going to completely break, right? Because you're not going to be able to do this element-wise sum if it's not going to fit in memory. Right? It's gonna page out, and you're going to start swapping, and you're just going to kill your performance. Right. So here's a fundamental limitation of this algorithm. Yep.
So is it the case that at the reducer phase you may have a lot of duplication in the different values that are sent to it, like if you have an associative array for one chunk, right? It could be almost every word in the collection, and then the next one could be almost every word in the collection.
Yes.
Like in that phase, it might even be too big as well. Right?
Yes.
Not just one array.
Yes. Yes. Well, it depends on how you actually do the sum, right? So yes, you're right. Right. Any other questions? Okay, so here's the performance of the two algorithms. So as it turns out, the stripes approach is a lot faster than the pairs approach. So this is running time in seconds on different fractions of the gigaword corpus, which is a standard corpus used in language processing. It's relatively small. It's 2.3 million documents, about 6 gigs. Okay, so you'll see that the stripes is the squares, and performance is many times faster than the pairs approach.
It's only one source in the gigabyte.
Yeah, one fraction of the gigawords. Yeah, APW. Okay. Damiano keeps me on my toes. Okay. All right. So the next thing, let's try a little bit more, get a little more sophisticated. Let's say we want to estimate conditional probabilities, relative frequencies. Right. So we want to find estimate the probability of B given A. Okay. So what you'll need to do is you need to count the co-occurring and divide by the marginals. Right. So you need all the count of A and B divided by all the count with A associated with all other possible B's. All right? Okay, so why do you want to do this? Well, because counts, absolute counts are not what you want to work with because words occur with different frequencies. Right? Some words just are more common than others, so think of it as normalization. Right? And so the question is how you do with MapReduce. Okay? Well, with the striped approach, it's real easy. Right? Because you already have all the B's that are associated with A. So what you do is once you sum up all the B's, you do another pass, and you simply divide through by the sum. Right? More technically, you can compute the marginal right there, and then you divide through by it. Right? Okay. How do you do it in the pairs approach? Well, it's a little bit tricky, but it provides a great case study of how you orchestrate your MapReduce algorithms to handle relatively complex synchronization problems. Okay, so here's what you want to do. You want to, so the idea here, you have to orchestrate your process such that the marginal comes first, right? The marginal is the denominator that you want to divide everything through by. Okay, how do you make it come first? Well, you can control the sort order. Okay, so you do two things. Well, you do three things. You do four things, actually, sorry. But the first thing you got to do is you got to count the marginals also, right? So with you got to emit an extra A with a special symbol star, which represents a marginal, every time you see an A. Okay. You also have to make sure that this guy comes first, that this comes first in the reducer, right? Because you want this denominator to get to you first. Okay. And then once you make that happen, inside the reducer stage, you can simply say, OK, I've gotten the value. You hold it in memory. And as you process the rest of the reducers, you simply divide through.
But can I ask?
Sure.
Yeah, but all the reducers got these at the same time, so there's no way of getting that first because when all these numbers reach the reducer, A common star would be there.
So in MapReduce, let me try to explain a little bit more detail to see if it still helps. So all the keys come in a sorted order, right? So the MapReduce runtime, as part of the API, you define a sort order that tells you what order the key should come in. So essentially by defining the sort order in the way that you want, you can orchestrate your computation such that the thing you need comes first. And this is exactly what we're doing here. We're orchestrating the computation. We're essentially taking a synchronization problem and turning it into a sorting problem. Right, so you orchestrated that the A star comes first, and once you have it inside your reducer, you're going to process the rest of the A-B pairs. You're going to simply divide through and emit the conditional probabilities. Okay. One final piece is that you've got to make sure all the A's go to the same reducer. Right? That might not be the case because by default, what you're going to do is you're going to take the hash value of the key. Right, so you're going to take the hash value of the key and mod it by the number of reducers that you're running. Okay, so it might be the case that this guy goes here, this guy goes there, this guy goes there, and then it won't work. Right, so basically, you have to write a custom partitioner such that all the tuples that have the same left place go to the same reducer. Okay, so here's a great case study that shows the illustration, that shows how you can use all these tools to turn a synchronization problem into basically a sort order problem. And then once you get the data that you need in the correct sorted order, you can simply do whatever it is that you need to do in the reducer. Yep?
Yeah, I just want to try to put you on the spot. Right?
Sure.
So like in conditional probability, you only need to divide by the marginal frag. But
Yeah.
if you want to do, say, mutual information, you may also want to divide by the marginal for B. Have you thought about maybe a way to do that in one shot?
Yes.
Okay.
Yes. I'm working on it right now, actually. So we can take it offline.
Okay.
But Yes, I actually have a student working on this exact problem that she's going to write out. Yep.
You could also move these over to the value side and the value base tuple to avoid that sorting issue.
Yeah, sure. I mean, there are multiple ways to do it. I just think, sure. Yeah, I think you're right. Okay, so basically these two pairs and stripes approach formulate a sort of a very nice case study of how you handle synchronization in Hadoop. Right, so we started off with the complaint that, gosh, you don't know what's going on, right? You don't know where the mappers are doing, you don't know what the reducers are doing. But the truth is, yes, there are tools at your disposal for controlling that. So the approach one is to turn synchronization into an ordering problem, as we talked about. The second is so that's illustrated by the pairs approach. The second is the stripes approach, where you basically construct the data structure in a clever enough manner such that all the pieces of data you need for your computation are brought together in the same value. So you don't need to deal with all this complex sorting and shuffling. All right. Okay. So let's see how we're doing on time. Oh, perfect. Yeah. So there are just these trade-offs that you need to think about: the number of key value pairs versus the size of each individual key value pair. The serialization, deserialization overhead of moving very complex objects around the network. The difference between your usage of RAM versus disk and network. Right. Okay. So, any questions? Good. Okay. So I'm going to move on and present a very quick case study in statistical machine translation. This is a student that I've been working with in University of Maryland, Chris Dyer. Damian certainly knows him. Probably nobody else in the room does. But anyways, he's been working on statistical machine translation algorithms with MapReduce. And I'll sort of present a case study of cool results that we've gotten. Okay, so statistical machine translation, right? It's very simple in theory. It's complex in practice, right? You're going to just maximize find the English expression that maximizes this expression, right? Translating for the most part from foreign language into English, right? So modern, you guys had a session on StatMT previously, right? Okay. So as you've learned, phrase-based machine translation, what you're actually doing is breaking up the source sense into each individual phrase, and you're translating each individual phrase individually, and you're basically trying to put everything back together again, right? So graphical illustration is this, right? So you have you look up in your phrase table all the various possible translations of different phrases, and the translation is actually, you can think of it as a tiling problem, right? Where you find a tiling of these phrases that matches the input and subjected to the condition that it's got to be good English, right? And the language model tells you if it's good English or not. All right. Okay, so here's a typical MT architecture. You start with parallel training data. You go through a word alignment process, and from that you extract out the phrases. Right, and that goes through your translation model. You also take a target language text. This is monolingual now. You can build a very large language model, and these are the two components that go into your decoder. Right. In the previous slide, the translation model basically tells you what the tiles are, and the language model tells you if the tiles you've assembled are good English or not. And the decoder has got to take into account both constraints. Right. Okay. And so once you have the decoder, you can translate. Okay, so here's the data bottleneck. On the x-axis in this graph, we have the number of sentences used in the training data on the parallel language training data. And on the y-axis, on the right here, you have translation quality, and on the left here, you have running time. Okay, so you'll see that translation quality increases. This is blue score with the number sense. Right, this makes sense. The more data you throw at it, the better your system gets, holding all things equal. Okay. The other thing that you'll observe is that as you work on larger and larger data sets, the running time increases. Right? So that by the time you are working with all the data you have, it takes about 2 days to train up a model from scratch. Okay. So this means, what does this mean? this means that if you have an idea, okay, I want to work on this part to improve MT performance, you got to wait until 2 days. You got to wait 2 days until you find out if it works or not. Right? So imagine, having a great idea, hacking up some code, and then twiddling your thumbs for 2 days while the experiment is running. All right, so this is not very efficient. It's not a fast way to get a PhD. Okay. So Chris looked at this problem, and what he's done over the last 2 years by now is built a MapReduce implementation for these two components, the word alignment problem and the phrase extraction problem. Okay, and the only reason one of the major reasons I also went over through that example, the pairs versus stripes and computing conditional probability, is that the MapReduce algorithm for the word alignment process is not very different, right? There's more math involved, but at the end of the day, it's a large counting problem. It's a large counting problem where you see words in English and words in French, and you gotta make some inferences about co-occurrences. Right? So the math is a little bit hairier, but it boils down to exactly those techniques we talked about before. Okay, so let me share with you some results. So here is a standard off-the-shelf toolkit for doing MT. It's called Giza Toolkit. You can download and play with it. Here is the size of the corpus, and this is the running time on a single core commodity server. These were run 2 years ago, so it's a lot faster right now. But this is per iteration of this algorithm. It takes about 3 hours with all the data we have. And typically you run half a dozen iterations. So this means that for this phase of the alignment process, you have an idea, you hack something up, tomorrow you'll know the answer. Okay. So what Chris did is wrote a MapReduce implementation, and here's the running time of the MapReduce implementation on a cluster of 38 processors. Actually, these things are single core, so 38 cores. Hey, you see, we've dramatically reduced running time from 3 hours to 3 minutes. But hang on, wait, you say, that's not fair. You're comparing one machine against the entire cluster. Okay, fine. So why don't we do this? Take this time and divide it by 38. What does that mean? That means if I had an optimally parallelized code and it runs in an optimal fashion, if I run it on 38 cores, it should run in 1/38 of the time, right? This is optimal linear scaling. Okay, and that's the reference here. Okay, when you're dealing with small amounts of data, doesn't make sense to compare, but MapReduce really loses because you waste a lot of time in doing the setup, right? But you'll see on the data that we have, on all the data that we have, you're getting pretty close to optimal scaling. Oh, fine, it should take only 2 minutes, but it takes 3. Oh, wow. Okay, I can wait an extra minute. Okay, all right. So what's the point? The point is that this optimally parallelized version doesn't exist. Okay, there's no parallel Giza++ that runs this fast, this standard toolkit. And you know what? I bet you that if somebody tried to go out and implement this optimally parallelized version of Giza, probably doable, but it would take a lot longer than the time it took Chris for him to implement the algorithm in MapReduce. Okay, right. So it's all about the right level of abstraction, right? So this is a variant of the Goldilocks algorithm, right? So for any particular algorithm, you can engineer it to death and squeeze every ounce of performance out of it, and you'll likely run blazingly fast. But at the same time, you want to ask yourself, was it worth all that effort to do all that detailed engineering and the time you spent? Whereas on the other hand, MapReduce provides a level of abstraction that's much higher that allows you to write algorithms in a much simpler way that'll distribute very nicely onto large clusters. Okay, so good timing. Any questions?
Of course, if you spend 10 million sentences, this relatively different
Yep. Okay, so what's next? So I think what we're going to see moving forward is that web scale processing is not going to become a luxury anymore like it is today. It's going to become a necessity. Right? If you want to do anything interesting, you got to do it on lots of data, or otherwise people are not going to pay attention to you. They'll simply say, "Oh, that's a toy data set. All your results aren't going to scale up, and they're not going to be are not going to be meaningful." All right. So, but fortunately, if you think back to the first slide, with the advent of cheaper machines, alternatives like utility computing combined with MapReduce as a programming paradigm, basically the resources and the tools for using that resource, anybody can get there. Right. How many of you have heard of EC2? Okay, EC2 is a service by Amazon where you can literally sign up for an account, put in your credit card, and rent clusters by the hour. 10 cents per processor core per hour. So a 100 core processor costs you $10 an hour. And so you go in, you fire up your processor, you do it for crunching, you use it for crunching, you release your resources, and at the end of the month, you get a bill for how many processor hours you've used, essentially. It's like an electricity bill. It's a very different way of thinking about a very different way of thinking about computation. So MapReduce is a very nice hammer, and I think what everybody doing, including myself, is taking this hammer, now that it's an open source and everybody has access to it, and basically whacking on every problem in sight. Okay, but I think this is only the beginning. There are going to be lots of, it's an exciting time to be alive, as they say. You know, everybody in every era says that. But I really think we're really on the threshold of this commoditization of web scale processing. There are going to be further alternative processing models coming down the pipe, going to require fundamental breakthroughs in algorithm design. So here's how I see the picture evolving in the future. So on the top, what you're going to have is driving applications. So applications in NLP, you're driving applications in information retrieval, and machine learning, and text mining, in vision and graphics, whatever. Okay? And at the bottom, you're going to have systems, actual hardware, and people that work on systems architecture networks. And then the ecosystem is such that you will have the development of programming models that mediate between the applications and the systems. Okay, so MapReduce is only the beginning. People are already asking themselves, okay, what's the next thing beyond MapReduce? What other programming models can I have to abstract over entire data centers worth of machines? Okay, and you're going to see two competing forces. Well, not competing, two complementary forces. From the top down, you'll see complex applications that drive the development of new programming models that then lead to innovations in systems and networks. Right? So I want to crunch, the application person says, I want to crunch more data, and says to the programming languages person, who in turn talks to the network person. How do I make this happen? Right? On the other hand, you're going to have this upward pressure also, is you're going to have developments in new systems and architecture that leads to new programming models that allow you to solve new applications. So a great example of this is GPUs. Right? GPUs is an innovation at the hardware level, but mediated through programming models like CUDA, have allowed people to tackle applications in ways they weren't able to before. All right. That's about it. So, of course, a nod out to all the organizations who support our work down at Maryland. And 11:58, perfect time. All right, 2 minutes for questions. Yep.
So one of the things I've been impressed with about MapReduce is how flexible it is. So there are tremendous, you gave a bunch of examples, but a tremendous number of things that you need to do that don't seem to have anything to do with MapReduce that you can reduce out of this model. What have you found to be some limitations, though, of this model? What sort of things are just really difficult to do?
Great. So anything that requires global state is something that's incredibly difficult to do. Okay, at the risk of losing some people in the audience, for some of these iterative algorithms, you need to distribute the model. Right? A lot of these algorithms start off with a model, and they essentially update parameters to that model. Okay, all right. So I don't think I've lost anybody yet. But the problem with this is, the question then is, how do you distribute this model? How do you distribute these parameters? Sometimes for these models, there may be billions, even trillions of parameters. Okay. The simplest way is to package up all the model parameters and push it out to every node. Okay? What's the problem there? It's limited by the amount of memory on a particular machine, right? Because you have to hold these model parameters in memory before you can operate on it. All right, so at some point in time, these models are going to get so big that you won't be able to move it out to. They won't be able to fit on the machines, and then you run into a bottleneck. Right, so there are other solutions. So there are distributed databases that can get across. There's different ways of dividing up the models into smaller pieces, but that requires more ingenuity. So that's an example. That's a specific case of the problem where you need to access global state in each one of the mappers, and that's a problem.
So actually, to take that example, so the approach in the learning community to that problem has been to assume that we're never going to be able to do this correctly. And what we need to do is we need to have independent algorithms that we can then combine the output at the end.
Sure.
But we haven't figured out how to do that.
Yes. Well, so it's solve one problem or the other, right?
Basically, a lot of people have been frustrated by how difficult it seems to be. That no matter how smart you get, you can't beat having access to the global state.
Yes. Yes.
So. Should we keep working on that, or do you think there's going to be a solution?
Well, so the solution is a distributed key value store, or distributed database. This is where how many people have heard of Bigtable? So a variant of Bigtable solves this problem for Google. So the problem is that there is no comparable open source equivalent that solved the problem. So I guess the short answer is yes, Google solved the problem, but no, the rest of us don't have access to it because it's still.
Bigtable is not nearly fast enough, I don't think, to do this sort of thing.
There's an
thousands of parameters for every key.
Inside the so there is a option. There's an option in Bigtable where essentially move everything into memory. So everything is served from memory, and there's actually a system like Bigtable Lite. It's Bigtable Lite, but it's not exactly Bigtable. That allows you to pay relatively low cost and accessing these parameters in a distributed fashion over the network. So that's a solution. I don't know. Beyond that, it's an active area of research is all I can say. Right. Yeah. Do we have any other questions? Okay. Oh.
Do you think HBase isn't ready for HBase being open source?
Last time I played with HBase, which is the open source clone of Bigtable, which was admittedly a few months ago, I don't think it was ready for prime time yet. I don't know what it is today. HBase, the primary developer behind HBase is PowerSet, which recently got bought a while ago now, actually, by Microsoft. So and has worked its way into Microsoft core search technology. So it's unclear how Microsoft is thinking about this open source component of their infrastructure. So
within the HAL, there was an interest in making computation of those values something iterative, so that they could continually append something. I don't know if it was successful, but there was an interest in changing how those are computed so that they could change the grain with using HBase time around.
Oh, okay.
And
Yeah.
PowerSet also.
Yeah, I've heard something about this, but these are open source projects, right? I mean, these are people volunteering their time, unless there's a big corporate, backer. For example, Yahoo is a major corporate backer for Hadoop. Yahoo actually has full-time engineers dedicated to Hadoop. I guess HBase does also, but I don't think Mahout does. Mahout is a bunch of people's weekend projects, right? So who knows? But it's exciting. I mean, I think eventually this is primarily a question of maturity. All these open source tools are are nowhere as mature as the tools that are available inside Google. But that's fine. I mean, that's just, yeah, we're all playing catch up. I readily admit that. But the exciting thing is, we all have, through Hadoop, we all have access to a reasonable facsimile of the technologies necessary to operate on literally multi-terabyte collections. Okay, thanks a lot, guys.